And Veolia Water has been doing a substantial amount of work and research on this over the last several months. I know that there has been a huge level of intensity in terms of their information. And we're very pleased to have Laurent Auguste, who is the president of Veolia Water North America, here to really present that overview of that information. Laurent oversees Veolia's operations in the United States, Canada, and the Caribbean, with additional responsibilities in South America. He began his career in environmental services in Tokyo in 1991 as a consultant before joining Veolia Water as a branch director in France in 1995. Since then, he has also served as president of Veolia Water Korea, where he developed and signed contracts with several global industrial firms that still serve as some of the parent company Veolia Environment's largest contracts to date. In 2008, Laurent became president and CEO of Veolia Water North America, which serves approximately 270 municipal industrial customers and population of approximately 15 million people. Their largest single contract is with Metropolitan Milwaukee Sewage District here in Milwaukee. Veolia Water North America has been a strong supporter of the Water Council's work, and Laurent serves on the Water Council Board of Directors. And I can attest, I don't know if this man sleeps at all, because I will be getting emails from him constantly and replies at all times of the night. What does that say about me then, if we're actually communicating? But Laurent was very instrumental, and again, being able to pull together the speakers for today, and very, very helpful. And I think you'll be extremely interested in what the information that they're going to be presenting. Laurent Auguste.
I guess we had, wonderful speeches and interventions today. And what I would be trying to do is to take it a bit closer, to some extent, to data and to facts here in Milwaukee. This picture, the Great Lakes, a wonderful lakes, beautiful, 20% of the world surface fresh water. This essential element for life and any economical activity. Looking at this picture, I find it actually amazing that such important part of the world water is actually gathered in some fashion in such a limited land. As we know, there is an increased depletion of groundwater in more and more locations, such as Florida. So, as the Great Lakes represent 20% of the world freshwater, let's imagine for a second that 20% of the world population would gather around the lakes or depend on them. It will mean 1.2 billion people, 4 times the current population of the United States. And with the current trend in population increase, in a few decades, 1.8 billion, 6 times the current population of the United States. All of a sudden, these lakes look much smaller and even vulnerable. Lee told us this morning about the Aral Sea case in Kazakhstan. It used to be the 4th largest lake on Earth, larger than the Michigan Lake. Over 50 years, this lake has lost 90% of its surface. Milwaukee has been a pioneer in understanding the value of freshwater as an asset, and is the first city to be recognized by the United Nations for its action towards efficient freshwater management. What I would like to share with you today is one more step in this global leadership in freshwater management being made here in Milwaukee. Nowadays, there are a variety of ways to make fancy steps. But it seems that it's getting even more fashionable to focus on footprint rather than on shoe. There is the economical footprint, the carbon footprint, and now the blue footprint. So what is this new step about? Actually, 2 words first. 2 tools to support decision-making for sustainability. The first one, the Water Impact Index, a new index that will enable to assess the level of impact that an activity or a product has on freshwater resources. It covers the 3 essential elements to evaluate this impact: the quantity of water used, the level of stress under which the water resource is, and the water quality. Secondly, a simultaneous analysis of the economic, carbon, and water impact to support decision-making grounded in sustainability. So it means a new comprehensive footprint model and a new step in Milwaukee leadership in freshwater management and sustainability. So let's look a bit into the details. And first, let's try to understand why the carbon footprint matters. Obviously, everybody has in mind the climate change concern. But there is also the fact that from a resource perspective, we are about to witness the end of the world as we know it today. The world energy consumption has been multiplied by 10 in the past 60 years. And the vast majority of this energy comes from fossil fuel, coal, oil, or gas. These are non-renewable sources of energy. It means that their availability is limited. And so our ability to produce energy out of them will reach a maximum in some point in time. As far as oil is concerned, this has been already the case in the US in the mid-60s, and also more recently in various locations such as Norway or Indonesia. Many experts estimate that the global peak of oil production will be reached by 2015, which is basically tomorrow. So we can say, okay, there are alternatives to oil with renewable energies, and so we will just need to switch to these new sources of energy to compensate for the lack of oil. As the graph shows, the difference in order of magnitude in production capacity between oil and renewable energy is such that we are actually very far from being able to replace oil by renewable energy. And so, in the midterm, gas and coal will be the only alternative to oil. This will mean more CO2 emissions. A Japanese professor, Kaya, came with this wonderful equation. CO2 equals CO2. I'm sure everybody is still following. But pay attention, it's going to get a bit more complicated. If you multiply and divide by energy in tons of oil equivalent, the equation is still valid. If you do the same with GDP, and then with population, we now start to get something fairly interesting. The CO2 emission equals the carbon content of energy supplies times energy efficiency of the economy times wealth per capita times population. As for the climate, it is estimated that we should consider dividing by 2 our current CO2 emission, and that we better do that before 2050. What does it mean for the rest of the equation? The population is supposed to be multiplied by 1.4 by 2050. The wealth per capita, we expect that this will grow. If we have only a 2% growth per year, this will mean a multiplication by 3. So to balance the two sides of the equation, what you need to do is actually to divide by more than 8 the two other factors. It means that we need to improve significantly our carbon efficiency. And as we cannot act effectively on what we do not know, to have a chance to do this, we need to measure this carbon emission, and this is where the carbon footprint is necessary. So what about water? Unlike oil, there is no substitute to water. And unlike oil, transporting large quantities of water is not a practical option. In Wisconsin, the annual per capita consumption of oil is of 8 tons. But it is of more than 2,000 tons for water. It means 250 times more. It would take a lot of energy, and by the way, a lot of CO2 emission, but also huge cost. And huge infrastructure to transport water as we do for oil. We can hope from one oil field to the next if we have exhausted a resource. But we cannot do the same for water. And so we need to manage properly this resource in each location, or the consequences can be dramatic. Water can be consumed in two ways. The obvious one, withdrawing it from the resource and returning less. And obviously, you have to care about the balance if you don't want to dry up the resource. But you can also consume water by polluting it. And the consequences can be very severe for the environment, but also for the economy, as unfortunately we are witnessing it in the current BP crisis. So if we come back to the now famous Kaya equation, and that we start applying it to water, we get water consumption equal the water efficiency of the economy times the wealth per capita times population. We cannot draw exactly the same conclusion for this equation as in the case of carbon, because there's no global conclusion to take out of it, because water is always specific to the local issues. But locally, water can be limited as a resource. And now local growth expectation would require an increased efficiency in water consumption and a locally controlled impact on water resources. Here again, to do it properly, we need a metric to measure, understand, and enable us to make the sustainable choices. Hence again, the importance of the footprint. Now that we understand why footprint assessment can be very useful tools, let's get a little bit more into the calculation. If you have read the wonderful April edition of the National Geographic focused on water, you are familiar with the concept of virtual water content of products. If you have not read it yet, I really encourage you to do it, and I'm sure that Paige or Dennis can get you a few copies. This water footprint representation is great. It is a great way to make us aware of how much water it takes to produce goods and to start leading us in our consumption options. However, looking at the volume of water only may not be sufficient to guide us accurately in our consumption options and to represent the impact of that these products have on the water resource. Let's take an example to explain why. And for that, let's look at the embedded water of two products. On one side, the tomato sauce, on the other side, peanuts. So looking at the volume of water needed to produce peanuts, it appears that peanuts have the worst impact compared to tomato sauce on water resources, and actually about 6 times worse. But actually, if you start factoring it, the level of stress in the water resource, the conclusion is completely reversed. The impact of tomato sauce is 10 times greater than peanuts. Why is it so? Peanuts are actually rain-fed, come from a rain-fed agriculture, when tomato requires irrigation, and very often tomato are grown in water-stressed areas. You need also fertilizer for tomato, which means pollution, and as we've discussed, to some extent, impact on the water resource. So actually, looking only at volume can mislead us in our conclusion as far as the water impact is concerned. And you need also to take into account the stress of the resource and the quality element. And there are obviously a lot of different examples that we can take. For instance, take the case of beef. Although the water necessary to generate 1 pound of beef would be the same whether the beef is grown in a water-rich or a water-poor area, its impact on the water resource will obviously be quite different. So to be accurate in our representation, we need to look into a bit more details than volume only. This is why Building on this initial very good representation based on volume, we thought at Veolia that it was necessary to bring it to the next level and to introduce a new metric to assess the impact on water resources. This is what the Water Impact Index does. It is measured in gallon per Water Impact Index equivalent. And it captures volume, the level of stress of the resource, and the quality. How is it calculated? Fairly simple. You take an industrial activity. You've got to identify the volume of water that you need to input and the volume of wastewater that will be discharged. But you need also to weight this with the quality aspect and to multiply all that with the level of stress to take into account the different type of resource that you will be using. It gives us what we can call the direct water impact. But to be comprehensive, we have also to add other water impacts of the indirect element coming into the full production chain. For instance, the raw material or energy, or at the end, the waste generated. It takes a lot of data, but actually it's pretty simple. I guess everybody would agree. Now that we have understood everything about the index, let's start using it. And let's start looking at the state of Wisconsin. When looking at the share of various water abstraction made in the state, we realize that about 80% of it is for power generation. So this could lead us to the conclusion that to improve the water impact in Wisconsin, we should almost slowly focus on power generation. But if we start applying the Water Impact Index, we realize that the picture is actually much more balanced, and that we need also to focus on other elements than power to improve the water impact on the resource. This can be irrigation, industrial activity, obviously, or municipal activities. What would it give if we compare two states, such as Wisconsin and California, pretty different states? If you look at this first graph, and again at the level of water abstracted per capita and per year, you find out that this level per capita and per year is 1.5 higher in Wisconsin than in California. However, when you start applying this Water Impact Index, the picture is completely different. And actually, so the per capita impact in California is 50 times higher than in Wisconsin. Obviously, this is coming from things such as what Bob was telling us this morning in terms of the electricity consumption, but also the fact that we are talking about a state that is under water stress. This map shows the water stress index. Obviously, red is not good. Blue is the location where there's less stress. And it's interesting to look at the fact that in the past 10 years, actually the red states have been having a lot of population growth. And I think you've got to ask yourself whether in the future water-rich states will become more attractive to population and potentially industrial activities. Now that the Water Impact Index elements are well established, let's go to our final topic of the day. And let's look at a study that we have made on the water and wastewater system in the Milwaukee area, with a review taking into account the water impact, the carbon footprint, and the economical aspects. Making this type of study requires a lot of data, a lot of time. And it would not have been possible without the leadership of Kevin Schaefer and of his staff at the Metropolitan Milwaukee Sewage District, but also the Milwaukee Water Works, the North Shore Water Commission, the Oak Creek Water and Sewer Utility, the Cudahy Water Utility, as well as We Energy, the University of Wisconsin, and obviously the City of Milwaukee. Thank you all. What we've done is that we've looked at the full water systems, from treatment for drinking water, all the distribution pipes, the collection system for wastewater, and the treatment of wastewater. So, what is the total water impact index of this water system? About 1,500 mega-gallon of water impact index equivalent per year. Obviously, you've got on the left the drinking water activity. This is where we take a lot of water out of the resource. Then comes the wastewater. And you see actually a reduced impact, because what we do is that we put water back. Obviously not to the same level of quality, and this is why this is not balancing. And what you want to do going forward is to try to reduce this impact. If we now zoom into MMSD, you see that the impact is coming on one side from, again, the water being discharged back into the system, a bit from the overflows, but there's a negative impact from the energy consumption and the chemical use, a bit also coming from the waste generation. And this is what gives you a minus 87 mega-gallon of water impact index per year for MMSD. There is actually an additional positive impact coming from meal organite. Everybody knows meal organite. Obviously, meal organite unable to offset the potential utilization of fertilizer. So this is something that you could consider to some extent factoring in. If we look now at the carbon footprint, still on MMSD, the footprint, the emission of CO2 equivalent a year is of about 230,000 tons, which is similar to the emission of about 11,500 people. And we see that the main part of it is coming obviously from the energy utilization, electricity or natural gas, the chemicals, but also the works activities, the construction works activity. If you look at both drinking water and wastewater treatment systems, the total carbon footprint is of about 310,000 tons of CO2 equivalent a year. That's about 15,500 people equivalent in terms of carbon footprint. Focusing a bit on the drinking water, you see that the balance between production and distribution is more or less the same. And if you focus on the distribution side, on the works part, the construction works part, it's interesting to see that actually the main contribution in terms of carbon footprint is actually coming from the nature of the pipe that is being used. So if you want to reduce this carbon footprint, this is where you've got to focus, maybe more than from other part of the system. What I would like to do now is to take a couple of examples where we have looked simultaneously at the carbon footprint, the water impact aspect of several projects. Overflows are always a very sensitive topic here in Milwaukee, and rightly so. The situation has actually improved dramatically since the completion of the deep tunnels, despite very heavy rain, 50 years rain, or even 100 years rain in the past 2 years. Before the deep tunnel, there were about 9 billion gallons of overflows a year. Now, it is down to less than 1.3 billion gallons a year. It means 7 times less. How does it translate in terms of carbon footprint and water impact? The graph shows the carbon footprint and the water impact for an overflow of 1 gallon of various types of water. If you start from the left, you've got the case of pure sewage overflow. Obviously, the worst case, and to some extent, historically, what was happening before. Then, if you switch to the right and to the next 2 columns, you've got the impact of a combined sewer overflow and the impact of 1 gallon of treated water after the treatment plant. And what you find out is that, obviously, going through combined sewer overflow, thanks to the deep tunnels and to the treatment plant, we are improving very significantly, we are reducing, very significantly the water impact, but at the same time, that the carbon footprint is actually going up. And this is because since the deep tunnels are in place, most of the water, including the storm water, are going through the plant, which requires, namely, energy. Finally, on the right, what we have is what MMSD is working on for the future. Stormwater will be going directly towards wetlands, which will avoid a lot of CO2 emissions while improving very significantly the water impact, actually about 12 times compared to the combined sewer overflows. More specifically, if we look at the 9 billion of gallons that used to turn into overflows before the big tunnels, their water impact has been actually reduced dramatically thanks to the deep tunnel, more than 4 times, as you can see on that graph. And so obviously this is a great achievement. Another very interesting and meaningful project developed by MMSD is the recovery of landfill gas for use in Johns Island treatment plant. What you see on the graph now is what would be the production of landfill gas. This landfill gas will enable to offset the use of electricity and as well as natural gas. And the impact will be, as we can see it on the graph below, in the curve in brown, the impact will be to reduce by about 60% the carbon footprint of these energy sources, and to divide almost by 4 the water footprint generated. And so this will mean a lot of saving in terms of CO2 emission, and these savings could actually someday maybe translate into dollars. If some days there is a cap and trade type of system put in place, or something like a carbon tax. And who knows? There might be in the future also something similar that will enable to monetize or at least to recognize the reduction being made in water impact. And we've got, to some extent, something similar with water rights in some states in the country. Another example, the phosphorus. This is a major element to take into account when assessing the water quality. And it has an important impact, obviously, on ecosystem. MMSD is now targeting to push further the quality of treatment, and by doing so, to reduce by half the phosphorus concentration in treated water. The impact will be very positive on the water resource, and it will also, but it will, however, increase the CO2 emission because we'll have to do more in terms of treatment, but this increase will be fairly limited compared to the positive impact on the water resource. Finally, a last example, let's look at a project of modification of the nature of some chemical used in the treatment. What we are currently studying is to switch from what's called the sodium hypochlorite to ammonium sulfate. Both on the carbon footprint side and actually on the water footprint side, this will have positive impact. It will actually, as you can see on that graph, also enable to save money. So it means that this will be a win-win-win project. Time now to come to a conclusion. I hope that I've been able to convey how important it is to look not only at the volume as far as water impact is concerned, but at the volume, the stress of the resource, and the quality element. And I hope as well that I've been able to give you a feel for the interest to look a broad perspective to make sustainable decisions. This requires, namely, to look at the balance of the economical aspect, the carbon footprint aspect, and the water impact aspect. Thanks to these studies, Milwaukee is making one more step in its leadership in freshwater and sustainability management. The blue footprint will lead Milwaukee to a smaller footprint and hopefully to a giant leap in global sustainability. Thank you.
this tool able to use for drawing industry back to Milwaukee when you compare what it takes to do the same thing in California versus here? Is there plans to use your tools for that purpose?
Yes, definitely. Yes, the question was, if I understood properly, is whether that tool could be used in other locations than Milwaukee actually to compare some industrial activities or different performances here in Wisconsin or Milwaukee compared to other locations, correct? Obviously, this is the intention to have an index that will enable to assess what is the water impact of various activities. You could imagine maybe someday to have labels on products that you would buy that will identify actually what has been the original impact of producing such or such product. And here again, you could look at, okay, how much water is embedded in the project, in the product, which again is a great representation, a great way to raise awareness. But if you want to take into account the way the product has been produced or where it has been produced, having an index such as the Water Impact Index that we are introducing today and that we've applied and developed for the first time here in Milwaukee could help and could help us to make the right decision to reduce the global impact on water resources. Maybe a question over there.
In the Great Lakes and the Milwaukee in particular, we've had a very hard time driving water conservation or sewage conservation because we have excess capacity, at least on dry days, in both those categories. Do you see this footprint, in particular the energy aspect of it, as being a driver that will allow us to achieve water and water and sewage conservation in our region? How do you see that applying there? Or?
Well, first, as a slide, keep in mind the RLC case. Keep in mind also maybe how the Great Lake Compact or Great Lake Initiative have been formed, with the fear that maybe because you've got 20% of the world water, the surface freshwater resource here in the Great Lake, that maybe a lot of people will need to tap into it. And all of a sudden you realize that this resource actually can be fairly fragile. So even in that environment, I think it's useful and important to pay attention to it. But as you're mentioning, the impact, reducing the impact on the water resource can mean also saving money, being more efficient, whether that's leakage on the pipe, whether that's the electricity consumption, whether that's changing the type of chemical. So taking the broader perspective can also help to understand why it makes sense to work on conservation. And finally, and I guess this is what is really gathering us all today, it is the understanding that this water resource is actually a great asset. And what do you do when you've got a great asset? You take care of it. You maintain it. So again, having a better understanding of how we are actually impacting the resource by our different activities, how this comes into the broader picture with carbon, energy, water. I hope that this is something that will enable to raise awareness, because what we need, obviously, is people to be more aware of what they're doing, what are the impact of their action on the resource, so that we move towards a better management of that resource. Okay.
Laurent, this seems wonderfully integrative, but it also seems very complex. How can communities, without the resources that you have, begin to better account for and make investment decisions that really do look beyond some of the individual factors we've used to date?
You found the Kaya equation complex? Yeah. Well, it's not that complex. I think the computation of all this data is, yes, it's true, it takes a lot of time. And actually, one thing we are currently doing is to work on building a database. Because I was talking about industrial products. Obviously, I mean, you've got to understand how much water it takes. And I was mentioning about the water stress index. That's something that you need to factor in. So you need to have some kind of database. But I think that in terms of indexes, whether they are technical, financial, we are doing a lot of pretty complex things. So the question is basically to put together this initial work that will enable then decision makers to have an easy access to this data and this understanding in terms of what is the impact. And again, the ambition that we have today with these two approaches is to provide tools to support the sustainable decision-making process. So not to make it complex for a mayor or a future governor to assess all that, but basically giving him or her the tools and the data that will enable him to make the right decision. At the end of the day, this is a political decision. At the end of the day, you've got to choose for phosphorus whether reduction of the impact on the water resource is more important than maybe increasing a bit the carbon footprint. This is a decision that has to be made by decision maker, but they need tools for that. Thank you for your attention.